So, hello everyone. Welcome to today's IStructE Northern Ireland and also the Republic of Ireland's Lunchtime lecture series. So, it's our pleasure to welcome our invited speaker, Dr. Teixeira. So, he's assistant professor from the Trinity College Dublin. Dr. Teixeira currently is the expert in structural reliability and probabilistic analysis with a strong track record in both academia and industry. His research explores risk and resilience in civil infrastructure, combining advanced computational methods, uncertainty quantification, and intelligence to support safer and more robust civil structure systems. Now hand over to you, Ray.
Thanks for the introduction. So I'm just going to share my screen to share the presentation, and you let me know if this is okay. Because I have two screens. Can you confirm that you're seeing the
Yeah,
the good
yeah,
the
yeah.
full
Looks good.
screen,
Yeah,
right?
yeah. Looks good.
Okay,
That,
good.
yeah.
So then I'm going to start. So welcome everyone. My name is Rui. Thanks for the introduction, Con. Um, I'm an assistant professor in the Department of Civil, Structural and Environmental Engineering at Trinity College Dublin. And today I'm going to talk about structural reliability and what I perceive or believe to be its role in designing to a highly uncertain future. That's a bit the reality we have today. So I'm going to follow a bit classical approach in this presentation. I'm going to start with introduction, then talk a bit about structural reliability and certainty, and then what are the methods? Some methods for structural reliability. There are many. Why they are so important when we have a context of increasing uncertainty, and then maybe a bit for the discussion, I'll start a couple of questions of threads on future prospects and new ideas in design. So for many years in the past, we assumed that, and we still do sometimes in some maybe simple projects, that loads and strengths are deterministic, or were deterministic. So usually we would have a certain action, a load in a structure. We would try to find what's the resistance to resist that load. And then we would say, okay, there's kind of, if that's too far from the load, we say there's a margin of safety. However, we know that there are uncertainties in the loads. This is whether the loads, strengths, and other variables in the structural systems. And usually, or in a number of situations, they require probabilistic techniques to be used. So if you take the newer codes and the further updates, they come with further and further ideas around probabilistic techniques, performance-based design. So for instance, the newer codes use the partial safety factors. We have a load resistance factor designs, and where we have characteristic values that, of course, are related to the uncertain loads and resistances and other variables. And the partial safety factors are applied to the loads and to the strength in order to ensure the structure is safe enough. So this is what we would call a semi-probabilistic approach. Well, these partial safety factors are usually, they could use expert elicitation, but most of the times they will use a reliability-based calibration. We also know that risk is quite prevalent in the structural systems. That's why we have classes. So if you take, for instance, the class 3, there's even a recommendation of a full risk analysis. This is related to robustness. This table was picked from a previous work a couple of years ago. I'm not sure if this was already updated, but again, just to show there's a relationship between the structural codes and the approaches we use in structures and the risk. And that's because of that, I think it's with no surprise that the typical risk of death associated with structural failures is one of the lowest we can find. So this has, of course, it's a bit older data, but we can see that for the exposure we have, the typical risk of death would be quite small compared with other daily activities that we can do or that we are exposed to in terms of risk. And I think that's a bit an indication of how successful we have been in terms of structural design and structural standards and so on. However, we know that we are in a kind of rapidly changing and challenging world, probably one of the most challenging that we have been in our history as civilization and society, and one where, in my understanding, structural reliability and risk will just increase in importance. So if we take risk, and we can say that risk is usually defined as the expected consequence associated with a given activity, let's say using the structure, that would be what's risk in that. In terms of risk accept or risk criteria or managing risk, usually we use the principle of as low as reasonably practicable. That's the LRP. It's sometimes the only acceptance criteria when we have a project and we need to do a risk assessment. Sometimes it's used against or with other risk acceptance criteria. So in practice, we have a certain risk. If we leave the risk untreated, that's going to be quite high. What we do is we apply a series of cost-effective control measures to reduce the risk until one point where further reduction of risk is just very disproportionate to the cost of further reduction of risk is just too disproportionate to the reduction of the benefit in terms of reduction of risk. And that's the level we say, okay, we have a risk that is acceptably low. And the reason for this is that to some point there's, it will become almost impossible to reduce the risk, so we cannot eliminate all the risks. And we don't want to crack a nut with a sledgehammer. So there will be one point where just the cost of further risk reduction is just too high for the benefits that we can get. So risk assessment would be used in a number of situations. And the general intention is to indicate that important aspects of uncertainties have been considered in some way or another. For example, taking structural systems, we can have an hazard, we have a response of the system, and we have the consequences. So this is this formula is extracted, or it's a simplification from a recently published book by Ellingwood and a couple of authors on risk of structural systems to climate change in that case. But we can see there's definitely a hazard, so that's going to create a demand in the system. We have a response, and usually we deal with probabilities. So that means we are we are working in the field of uncertainty. So things are, they can change, they can move, they have variability. So given that we have a certain probability of a hazard, we look at our response and we say, what's the probability of the response for my system becoming larger or smaller than a certain level, knowing that a certain hazard may take place. And then we do the same, knowing that this threshold has been surpassed or not. What is the probability of losses? And that's going to define our risk. If you take a view into this kind of triad, so consequences, these three strands, hazard, I think it's quite clear that it's easier to control the response because this is where the designers, as structural engineers, we can control the degrees of freedom and design our system to respond to certain hazards and to mitigate or to minimize consequences. So hazards are difficult to control. So if you think of climate hazards, extreme winds, flooding, so it's quite difficult to control in the design. Consequences are also difficult. So if you think of a bridge, that the bridge is commissioned for having to have traffic. It's and then there's an extreme wind, so you cannot control that hazard. It's an extreme wind, and then the consequences. Sometimes the bridge are closed, but we assume that they are designed to maximum utility, so we want to keep them using. So what we do is to control the response of that bridge to the extreme event instead of closing the bridge or trying to minimize the consequences on the bridge. And I think this is an important idea that response from a design perspective is easier to control because we have the degrees of freedom. Usually when we talk about structures, there's target failure probabilities, and they are given for ultimate limit states, and we can see how they may relate to the consequences of failure. So the larger the consequences of failure, the lower the probability of failure of the structure should be. And probability of failure is quite important in structural reliability because that's what we're looking for when we perform structural reliability. So what we want to look is to look at a certain structural system and try to define what's the probability of that system failing. In practice, we define that as the field of engineering that deals with the probability that a structure will perform its intended function over a specified period of time, that is, lifetime. That is under the condition it was designed for without failure. So in practice, it's just the structural reliability is the probability that the structure performs its intended functions in a specified lifetime. So there's a deep connection to uncertainty, and there's prevalence of uncertainty in engineering practice, so we know that. And it's critical, of critical importance in engineering design, in particular when safety becomes important. So applications, we have risk-based design, maintenance planning, design for safety or cost effectiveness. So in practice, in a nutshell, let's say, what we are trying to answer is, given all possible variabilities in operation and design, how confident are we that this bridge, building, tower, that is structure, will stay functioning properly during its lifetime? This, of course, has a strong link to safety. That is the condition in which a structure operates without causing unacceptable risk of harm to people, property, or the environment. Again, we are talking here at an acceptable risk, so this goes back to the idea that there's a level of risk that we need to accept at some point. This becomes quite important because the cost of engineering system failure is quite significant, even when there are no losses of life involved. If you look at some data, for instance, I've added here an example from the onshore wind from 2019, where the global onshore wind maintenance costs were estimated to be approximately 15 billion euros. And of that number, 57% was spent on unplanned repairs and correction of component failures. So this is a problem that we care because there's high costs, so we don't like failure. So before I go into the discussion on the reliability, I'm going to go quickly through the difference between deterministic versus probabilistic. So if we have a certain beam in a structure, we can assume, can have this simplification. It's a simply supported beam. There's a load P and two distances A and B from each of the supports. What we usually do is if we're doing design for the bending moment, of course, we try to find what's the maximum bending moment or a critical section. And we use this to pick a material or a section that is capable of resisting that bending moment. However, we know that there are many uncertainties in this process. That could be the physical uncertainty, so it's the natural randomness of quantities. That could be the yield stress due to production variability. Measurement uncertainty. So there are imperfect measurements. So we know that what we have on paper in the design may have some small variations to what's going to be built or installed on site. We have model uncertainty. If we use different models to estimate the loads, there's going to be some uncertainty coming from the model itself and from the gap it has with the physical reality, and we need to account for that. So there are this and many more. Usually we define them as epistemic uncertainties and aleatory, just for the sake of convenience, aleatory uncertainties. This one is presumed to be, or is one that is presumed to be as being caused by lack of knowledge or data, where aleatory uncertainty is presumed to be intrinsic randomness of a phenomenon. Why we divide them is because there's an assumption that this one we can always reduce epistemic. And the idea is that if we have some epistemic that again is by lack of knowledge or data, we can go and collect that data and reduce this uncertainty. And that can be one way to make our structure, to increase the reliability of our structure. The aleatory uncertainty is that one where further information may not reduce the uncertainty in the process. Let's take the case of throwing a coin, or throwing a coin would be a good example. So if we get more information about that process, it's not going to change the way that there is going to be a 50-50, or if it's an unbiased coin, 50-50 probability of it falling to one side or the other. So if topics of uncertainty are something you would be interested, I would recommend this read. where it's discussed that the convenience of this operation is discussed. And one of the interesting conclusions is that in practice, there's really no uncertainty at all, and just things we don't know, which I think is interesting. Now let's go, knowing that there are these uncertainties, let's go to the probabilistic case. So we had that load P, that A and B distances. Now they are uncertain, so we assume they are going to vary. There's going to be variability. This means that P is going to have a distribution. This is what we use usually, probability distribution to represent the uncertainty. There are other ways we could use interval variables and so on. A is going to have a distribution, and B is going to have a distribution. So that means that PAB divided by L is going to have also a distribution. And the material or the section we pick is also going to be uncertain. So there are going to be different, it's going to have the material capacity is not going to be a single value, it's going to be a distribution of values, and the section properties is, or the geometry of the section and so on. So usually in probabilistic modeling, we refer to this as random variables. So A, P, B, and we use probability distributions to approximate them. And then we have a limit state function. This is what we use in reliability. That is a function that will relate the resistance, let's say, with the action, the load. And if the load surpasses the resistance, we assume that we have a failure. And vice versa. Okay, so that means this is very interesting because you can see straight away that if this equation is negative, that means that this one term is bigger than this one, and then we have a physical failure. And the reason for that is because this is going to be a distribution. Let's say we are going to implement 1,000 of these beams. So we know that they are all going to be variable. So there could be combinations of beams and loads that will generate a failure. So what we do in structural reliability is to use these so-called limit state functions, and then we try to search. We know that failures occur when that equation takes a negative value, and we know that this fx is the joint probability distribution or density of the random variables of the problem. So it's going to be the joint distribution of these three variables, or all the variables you consider. So the probability of failure is going to be the density of this function over the region where the Gx is smaller or equal than 0. So in the end, is the combination of all the probabilities of x that generate a value of this limit state function smaller than 0. So what they're looking for is that small region over there. Over here, I think this is the intersection between the fs and fr. But when we combine them, so two things can happen, or if s is too big, or s is too big, and r is too small, so they will intersect, or vice versa, okay? Or this one is too small, yeah, it's the same. But in practice, we're looking for that tail region over there, and it's characterized by this integral over here. We also know there's a relationship between beta and the probability of failure, so it appears like this. We usually characterize the probability of failure with the beta. That's quite convenient because beta, or the reliability index, is just the inverse of the cumulative density function. So this is the same. Usually it appears more on this because we look for the probability of failure, but it's just the upper tail here. And beta is the number of times, or the number of times you had the standard deviation. So this is a standard Gaussian distribution. So it's the number of times the failure, or the number of standard deviations that are in between failure and the mean. Okay, so it comes from this equation. And then there's different interpretation of reliability levels. So we have target reliability levels. They can be related to human risk, perception, structural criticality, operation and maintenance availability, and then it's going to define all these beta levels. Just to say, different codes in type of structure have different beta, or will have different prescription of beta, and the probability of failure is related to that, so we can get one from the other. So let's look at the problem of structural reliability. considering what we just discussed. So let's say we have a shaft like this, we have a variable x1, it's uncertain, right? We have a variable x2, so this would be a load, okay? So I'm just keeping it simple, so it's also uncertain. Then we have this equation over here. So usually, so this is not from this problem, just to create an example or to explain how to solve the problem of reliability analysis for this shaft. So we have two variables. So these variables can take standard, let's say they can take standard Gaussian, standard normal values from, you can see here, 0 to minus something, 0 to minus something. And this would be, so this is a sample from the joint distribution of these two. They are independent variables, okay? So what we're looking for is, and then again, if we take one sample x1, one sample x2, so it's going to be a certain diameter or a geometric dimension of this shaft over here, then there's a load, and then we evaluate that in the limit state function, and that's going to be 1 point here. And that point could be, because these are standard normal variables, they can be anywhere in this region over here, x1 or x2. And so you have all these combinations are possible. We take one, we evaluate that, and we get 1 point here. And when we evaluate, let's say this is the shape of this function over here. So we know if this point falls here, it's going to be more or less here in the middle. So that's clearly above 0, okay? We do the same for another sample and another sample, and we start populating this region over here, and we get different evaluations of the performance function over here. Every time a point falls outside this red line over here, so this is the line of 0, so are these points over here, points that would fall over here, or points that would fall over here, we have a failure. And when we divide all the points that fall here in between, or when we divide this by the total number of points taken, we have the probability of failure for this system. So this is how we use Monte Carlo simulation in this approach. And the fundamental idea is that whenever we have a combination of x1 and x2, that's where variables are uncertain. So you can think you're going to install one of these shafts somewhere. So there's some likelihood that the probability of failure for this system, so there's some likelihood or some probability that you're going to install one of these shafts here that are going to fail, okay? So that's the idea here. And you need to know that in the design. So that could be, usually it is quite small, but it's still there. So to solve this problem of reliability analysis, this idea that so you can see that there's a strong connection to ones and zeros, because we can divide this. Every time we have a point that falls in this region over here, we can say it's 1 failure. And every time it's here, we can say it's 0 failures, okay? So that's important for later. So we can solve this problem with analytical solutions. So we just try to integrate this. Not always possible, because we may not have closed form functions for this. Another common method and very cost efficient is to use the first order reliability and second order reliability, where we linearized, or we have a second order approximation to the failure surface. We're going to see that later. Or we can use simulation methods that are exactly this. Okay, so we sample points and we try to find what's the probability of failure for the system. So in practice, what I explained is something like this. So we have different distributions of the random variables. We sample one from each, then we combine the 3 values here, and that's going to output, let's say we have a certain model that could be a CFD, that could be experimental. Of course, when it's experimental, we cannot do many experiments. That could be a finite element code. We combine the 3 values, we evaluate that in the code or in the model, or what the performance function you're using for your system, and then we get 1 point here. Okay, and then we repeat this over until we exhaust, or we have a good approximation of this function. So more and more variables, and we start populating this here. So what we are transforming is we are propagating the random variable uncertainty through the codes and getting the uncertainty in the output. So it's a problem of uncertainty propagation. So if we have, let's say, a CFD here, so you can think about that. So we have one simulation with 3 variables combined. Then we have another, And then, or you can think how this can become quite challenging. If we have a CFD, usually high fidelity models, they will need 10 hours or even days to run. So they are highly costly. And usually to find probability of failure are quite small. Okay, so you're talking about 1 in 1,000, 1 in 10,000. So that means for you to find that single point of failure, you need to run, for this one, you need to run at least 1,000 simulations. And you may run 1,000 simulations and nothing is going to show, because in the end, the probability, it's just an expectation of probability. So it may not show in the first 1,000 runs. So this can become quite challenging. I recall we were doing some work on a level crossing, and there was a very high fidelity model that took 48 hours to run. When we wanted them to work with that model to do reliability analysis, that was impossible. So if you think if you need 1,000 times a simulation that is high fidelity validated of 48 hours, that's just a lot. We cannot do that. It would take us, and even in parallel computing, would take us a lot of time. But the idea is then this becomes quite challenging because it can become quite costly. So that's why several methods have been invented. And we go back to this, so you can see to find these points of failure, how many simulations I needed here in this region. So I think this is the idea of this. So if we had a high fidelity model here, so I guess this would be 1 million simulations here. That, because the probability of failure is relatively small. And that's why we needed to start with new methods, or to develop new methods and research new methods that would allow this computation to be possible. So the idea of the SORM and the form is, again, to pick, because we don't want to run all the simulations over here. What we do, we have one point, we start at the center, let's say, or we can start with the sample, and then we start sampling and searching for a region where, or points where the response, or points here where the response is 0. So I start here, I see that it's quite big, the value of the response function. And then I move until I find this region of 0. When I find it, what I do is, if it's a first order, I just assume this is a straight line. Or if it's a second order, I can try to approximate this over here with the second order equation. Fundamental idea is that if I do this, then I don't need to run all these points, all these simulations. So I just need to run, I think I have here one example. So I just need, let's say here, so this is one example. So I need to run this, until I get that point, and that's where I start sampling. And this is also the same principle of importance sampling. Instead of going through or sampling through the whole domain, what I do is I search for the failure region. So this is the failure region. That means that for this system, if any combination of -2 with 2, let's say this would be in the safe domain for the system. Anything that will be on this line is going to be unsafe. So that's a failure. So the principle of importance sampling is very similar to the first order reliability method, and that's we shift the center of the distribution there. And with this, we can take maybe 20 or 30 times less simulations. So we concentrate our analysis around the region of failure, because that's what we are interested in. So there's no point in searching, well, I shouldn't say that, but there's, the information that is in this region over here, it's not very interesting for us because the failure is over there. So we are very focused on the failure region. And then there's more recently, and if you're looking into reliability, active learning is probably the way forward. So this has become quite popular in the last 10, 15 years. When these two papers were published, they were quite successful. And the fundamental idea is that we can search the exact, or we can have a notion of improvement. So if I'm looking for this region of failure, again, going back to the principle, so this is the performance of my function. Every time my system is operating in this region over here, it's safe. Every time it's operating in these 4 regions over here, it's unsafe. I'm really interested in separating these boundaries, knowing when the system is safe and knowing when it's not safe. But because there are so many points, and sometimes many variables, it can become quite challenging, that task. So what I do is I'm really interested in just characterizing this boundary over here or this border. So I'm going to search for points, or I'm going to look for measures of improvement that are going to define this border. Okay. I don't care if I'm not very accurate in this region. What I care is that the separation is perfect. And here, both of them use the Gaussian process. So this is a form of machine learning algorithm, I would say, where we fit a surrogate, and then that surrogate is going to inform where to pick the next point. And then we can divide this border. And it's been quite successful. And I mean, I think in terms of reliability, there was recently a benchmark. I think it was TNO, and I think it outperformed the other methods in many. I think it was 21 of 27, and still performed for all. So, what are the main challenges and opportunities for reliability? Having performance-based design. So instead of having prescriptions, instead of using the same safety factors, we can look at every single problem like this one, or like this. I'm going back to this. And then we can do a full probabilistic assessment. So I can know how these uncertainties propagate to the full uncertainty in the system. And then I can have a localized analysis with reliability formed by risk and reliability. Maintenance and aging of infrastructure. So this is going to take in the future increasingly importance over design. It's already used in calibration, or to check the safety indexes for structures that are already built. So we do some testing in situ, modeling, risk-informed decision making, because it allows to see the whole picture. So when you start working with risk, what it allows you to understand is to have this exploratory over the system, to know the consequences of the operation, and of course, digital twins and AI integration. So I think at the present, we can do real-time reliability integration. And this will change the paradigm of reliability engineering, because that's that very, very complex problem that I've just mentioned, that sometimes it could take months to analyze. With the most recent methods that can be done almost in real time. So I've seen recently something on real-time risk assessment, which I found it was for structural systems. I think that was quite interesting. Of course, then there's a trade-off of complexity versus utility. Should not be an issue because the benefits are significant. And when you play with the system, you analyze the different material combinations with load combinations and so on, you get more insight into the system. But of course, can still sometimes be quite complex for some projects, and that needs to be, of course, considered. When we have then highly uncertain environment, that's a bit what we have today. So we have usually a structural system, there's an input, a certain stimulus, it's uncertain, and there's a response of the system that is also uncertain. Let's say we have wind speeds, that would be one example. What we see now, okay. When we see now is that probably, for instance, the regions of the extremes here, so this would be a wind speed distribution. There could be changes here in the region of, we don't know very well what's going to happen in the future, but there could be changes here in the region of the extreme values. And of course, that's going to have an influence over the reliability of the system. And then this is the same as having an empirical probability distribution, or the distributions may shift slightly to the right, slightly to the left, and that's the kind of uncertainty we have. We always had uncertainty, but we have more, or one that is related to this shift in the patterns and so on. So if we look at this, we definitely have things changing in terms of the hazard. We have things changing in terms of consequences. So, structures that were built in the past for a certain demand now are being used at higher demand than that. We have complex hazard environments. And then, of course, we have response. And the problem with the response is that usually the civil infrastructure is thought for long lives. So when we make a decision, we commit that decision for 20 or 50 years, where that's usually where they are cost effective. So decisions are really important. If we take this environment now, and I have this with the highly uncertain environment, so with the highly uncertain future, I'm just going to use an example here. We can see the impacts of this. So I just have here a simple example, or one of the first examples is parallel. This is a parallel system. That means that when one of these, or when all of these three get values, or get combined values of smaller or equal than 0, then that's when the failure occurs in the system. Okay, and we have two random variables that, again, I just approximated. It's just used with standard Gaussian variable. It's a standard normally distribution variable. So you can see here x1. And then this is the performance function. So that means that the performance of the system is going to be described by the maximum of these three branches. If we take the reliability of this system when the probability is the standard Gaussian, and when the standard deviation of the system increases by 10%, so you can see here the response. So this is the response here, the full distribution of the response. You can see there's a peak over there, but we are quite interested in the area here, close to 0 here. Just when the system gets negative values, that's when we assume there was a failure in it. What we can see is that a small shift of 10% in this system, this is it's a complex system, and the principle is really to show this. If the system is complex, very small shifts in patterns, so this is 10% plus in standard deviation, which is something we can have in some of the systems we design in the future, means that this region over here, close to 0, can become quite populated. And if this region becomes quite populated, so this is, in terms of probability of failure, is a big shift. And so you can see here for this system with this small variation, we have almost 120% increase in the probability of failure. So we are talking about 1 in 700 expected failures to 1 in 300. So a 10% change resulted in a 120% change in a 10% change in input variability resulted in 120% change in the probability of failure for these complex systems. So when systems are complex, small changes can make a big difference. Just another example on extreme loads on a offshore wind turbine. So we have a monopile. Use this data over here. So this data is publicly available. So then assuming, let's say, a 10% increase in mean wind speed. So this is what happens with in terms of extreme load. So you can see here, well, the maximum or the maximal load doesn't change that much. This area over here becomes way more populated. And if we take a reliability, and so this is a 10% mean wind speed increase for both seasons, you can see that this area over here becomes way more populated. And in terms of reliability, this could be a concern, because that means that if one of these wind turbines just falls on the shorter side of the resistance for the tower, this was a tower, so it's a fore-aft moment. So that means it's the moment that overturns this wind turbine. You can see that. So in terms from a reliability perspective, in terms of probability, this would make a change to the reliability of the system. Again, I think this is all to kind of make the case that we may need more exploratory designs. Okay, in terms of if we have a certain system, what I believe it's important is now to get real insight in how the system performs under different conditions. So this is just an example of a fragility curve. It's a probability of survival. So if I know that a certain variable, just to give the example, that if I know that a certain variable k may change, even if I don't know where it may change or what's going to be the magnitude of the change, it's always very insightful to know the shape of this curve, because I will know that, if I design with this level, if there is a small change, I'm going to move here, or if here, and that will give me more insight. This is another example of in-service capacity, the same principle. And the idea is that we should explore the variables, know which ones are important, and use them to address or to work with the probability of failure. And then I think this brings the question on robustness or flexibility. So this is one of probably the main ideas here is we can argue whether we should go with robustness or flexibility, or in terms of structural design, or a combination of both. Assuming that robustness is we try to design for we try to make designs that work in a series or a range of future scenarios so that the design is robust to the future uncertainty, or we design in a way that we can induce flexibility in our design, that is, find ways that we can change our variables to accommodate future uncertainty. And in a context where we don't know at all what may happen in the future, we may need to rethink the designs in a way that we can accommodate some extra flexibility in the important variables such that we can accommodate to future uncertainty. This is a bit the principle of dynamic adaptive pathways, very used in climate change adaptation, and is that when we can delay a decision until we get more information about the future, we may be interested in doing that to the point where when we have that information, where we are confident, that's when we make and we commit to decisions. Again, reminding that these systems are designed for 20 or 50 years, so they may need that extra flexibility if they are to be designed to kind of future-proofed to any future. We may design with robustness in mind to different scenarios, but we may risk or in the future, some of these scenarios may not happen in the future at all, or any of them. And I mean, I think that's a bit of a discussion that may be initiated in the future in terms of whether we try to make robust designs or we think structural systems to be more flexible in terms of accommodating change. And I mean, this is kind of concludes my presentation. So structural reliability allows engineers to quantify and manage uncertainty, not just design around it. So it's important to quantify it because you get the whole picture of the problem at hand. Probabilistic methods from safety indices to simulation enable smarter risk-informed decisions. We have new challenges: climate extremes, aging infrastructure, digital integration. They will demand a shift from a kind of constrained safety margins to adaptive performance-based designs, in my view, again. And I think that the future of structural engineering relies on resilient systems that balance safety, cost, and flexibility under uncertainty. Because again, we have this challenge of designing for very long lifetimes. And I mean, we cannot eliminate uncertainty, at least at the moment. So if you would read some of the literature, there will be one point in the future there will be no uncertainty because we will be able to monitor the full process in a system where we will know exactly what may happen next, but we can design structures that thrive within it. And thank you. I think this concludes my presentation.
Thanks a lot, Hui. Yeah, great presentations. Thanks a lot. So now we have any questions, so you can free to ask, or you can just type in your question in the chatting room if you want. Okay, so I may have the question to be the first. Okay, wait. So from my understanding, okay, so like the probabilistic design, it usually aims to, let's say, to ensure the structure is safe, right? And also cost efficiently, I would say, right? But when you're talking about the highly uncertain the environment in nowadays, let's say the extreme weather, the wind or flooding, whatever, and then we do need to consider that kinds of the, let's say, distribution come from those kinds of the highly uncertainty environments, right? So in this case, are we going to have the over design again? That means, are we going to, let's say, losing the economic or cost efficient design advantage comes from the probabilistic design? And then the final question is, how are we going to strike, I mean, the balance between, let's say, the safety, resilience, and also the cost? And then also considering the highly uncertainty, the environment we have. Yeah, this is my question.
Thanks. I think that's a very interesting question because that's what starts the discussion, in my view. Is
Yeah,
I think there's a bit of perception that in the past we used to over design, right? And that was bad.
yeah,
Um, when we start looking at results like these ones that I showed, it also shows that if you go too close to the perfection, where
Yeah.
things may change in the future, there could be a risk there. So I don't think over design is a bad thing, but I think having a good sorry, I don't think over design is positive because that's what we have been fighting so much in the last, I don't know, many years. Um, I do think that it's very important to develop when we design a system to develop a certain level of awareness
Yeah.
where you will know exactly when things change, if things change in the future, you will know exactly what are the risks associated to that. And that means that a very extensive analysis in the design phase, trying to eliminate structure or trying to eliminate um, dot or in the structural system that or sorry vulnerabilities that would be you don't want your system if any change happens you don't want the probability of failure to change dramatically like that example I showed, and I
Yeah.
think that makes a bit the case that you could allow that but you need to be aware of it. So if any change happens, and I think that that's the balance regarding the balance. Yeah, I think that there needs to be a bigger discussion on that. Is we can do robust designs that comes with a cost. Usually, they're not the most cost efficient, or we can think of the structural systems in ways that we may be able to reinforce them if needed, or just leave that allowance. But this is probably a bit more to the future. And when we talk about issues like climate change, we are starting to see that, let's say, foundations that are made to be increased in the future. So they are made today to allow a certain uh, extra capacity if needed, and that's probably there needs to be a balance in between both of them, definitely. But for me, the answer is really you need to be quite aware of what's your decisions, what are the implications of your decisions.
Okay. Thanks. Okay. Yeah. So I think we do have three more questions from the chatting room. Would you mind reading them and also give the comments from your expertise? Okay. We
I
have
missed you
one
for a
more.
second. Okay.
Yeah. You can take a look at the chatting room. There's some free comments from the
Okay, okay, yeah.
yeah.
So I can start with first. How are we supposed to integrate this complex math? Because I think when we look at the math, it may look complex, but in my opinion, they are quite simple to apply. So you've seen, you just need to, if you want to go on the most extensive way, you just need to pick the probability distributions and sample points randomly from them, following the distribution, and run in your simulation model. So you could easily do that. It's very costly. There are more, there are easier ways to do that. Um, but that's definitely could be done. There are a couple of, and I think it's becoming more prevalent now, and more companies are using it. There are toolboxes, codes that are quite reliable already to do reliability analysis. If you don't want to through the full extension of developing the reliability yourself, you just need to say what are the random variables, how is your performance function evaluated. Let's say you have a finite element, code. You want to look at loads in a beam, and you could use that. So it's a black box. It can become a black box problem. Of course, I always recommend you to be aware of what's in between or inside that black box. Um, but I wouldn't call that a complex math. May apparently complex, yes, but in terms of application, I think it's quite straightforward to apply. If you start working with it a bit and applying it, you would see that's what happens. Well, the greatest challenge of existing buildings, that's a complex question. But I mean, there's, having a good, so if you want to do a very accurate reliability assessment, you need to work with uncertainty. Sometimes you wouldn't have information about the variable, so you need to have assumptions. So I mean, information, it would be a challenge in that regard. Some buildings are not well documented, or since when they were built. Um, so that could be information could be one of the challenges so that you have a high fidelity model. Of course, it takes work, a lot of work. It's becoming more widely applicable, but it still demands a significant amount of information if you want to get insightful results. And I mean, that would be probably the current challenge or the biggest challenge at the moment. So there's why don't we use form for higher accuracy? The problem with form, and like the example I've shown, is it may struggle with complex problems. It works very well, and there's a discussion on whether would always work on higher dimensions, but it works very well. It's very cost efficient, but it won't suit every single problem. That's one of the challenges. So if you do Monte Carlo simulation, that's very likely to suit your needs. Doesn't matter. You don't need to know the shape of the function or the shape of the problem you're working. You don't need to know if it's a complex problem or not a complex problem. While the form, it may be applicable only in limited situations where there are variations. So if your structure is only has one region of failure, that should work. If it has more than one, it may not capture that second region because it's a linear approximation, for instance. Again, digital twins, it's just a representation of it's a real-time representation of a model. I know this is a very crude simplification of the term. I know there's way more than that. There's shadow twins. But the fundamental idea is that in the end, this is if there's a big chunk of information theory here when we talk about probabilities and so on. So that means that digital twins are just a way of getting more information about a system. Okay, and that means if we get that information, we can have that information fed into a model and do real-time probabilistic assessment. That's probably what's going to happen in the future.
Yeah. So there's one question from David
Yeah.
Lin asking about how do I introduce the structural reliability analysis into the design and the reports.
So how do we introduce structural reliability analysis into design of reports?
Yeah.
I mean, in terms of practice, you would need so to I think it follows a bit what we do today in terms of reports for structural systems because you use the partial safety factors in here. You would need to detail your assumptions or the information you have, whether you're measuring the material strength, the loads. So it's going to be quite similar to what you do in a risk report. So where you do your probability assumptions, what methods you're using to calculate reliability and what results you're going to have, and then probably sensitivity analysis. So I'm not sure if this answers the question, but I think the most important is to be very transparent in the assumptions you have, what distributions you have used, what models you have used, and then be quite exhaustive in the limitations that you have in your reliability analysis.
Yeah. So due to time limited, so would you mind just address last two and then we finish today? Second last is more about the British standards. I'm not sure if you know that standards talking about more about structures in the line with extended design.
I mean, I can mention that
Yeah,
prescription,
yeah,
there's always a risk of a single prescription to all structures. So I think there's an advantage on, if it's a class tree, you can, and there's a recommendation to do more detailed analysis. That means you have more or a higher probe or a higher likelihood of getting a design that's going to fit your specific purposes. So the risk of prescription is you may be too far away or too short of a certain capacity. And I mean, for me, of course, if this if there is cost benefit in this, it's always good to have a very tailored and specific analysis to a certain problem. And then the design parameter variability. So let's say it's drift again. That's the principle of epistemic. So you need to get more information, and that would, I think, depend a lot on the. I think that would depend a lot on the problem at hand. So there's you can see what's the impact of the distance between the distributions. Again, this could feed into this need for flexibility. you may need to go there and have extra information so that you calibrate your model.
So I hope all questions most got answers, and but time is limited, and we have to end in this lectures today. Thanks again, Luis, and thanks everyone for joining today's lectures. So I will see you next time.